Hello, Johnny.
Hello, Joe.
I'm back here again.
I can see that.
I'm here to pick your brain again.
Thank you.
We are running into more and more requests from the logistics and e-commerce industry and dealing with all different type of cardboard material.
Yeah.
And as you know, we worked a lot with metal, and we feel we are quite familiar with how to design a vacuum system for picking metal sheets. But with cardboard, it feels like there is more challenges, and we can also see there is a lot of different quality, especially in the logistics and e-commerce, where there's a variety of different boxes and different cardboard quality. So maybe we can talk a little bit about that today.
Absolutely, certainly.
So could you just, maybe we can do some tests on these cardboard materials, but I see you have a metal sheet there first.
I prepared a little bit for today, and we have a metal sheet here that we can see the cartridge or the vacuum pump, the maximum vacuum, so we can get this comparison. Materials like this will always leak in some certain ways, and they can vary quite a bit.
Yeah.
So let's test on this metal piece first. And you should reach maximum level here for this.
More or less
cartridge.
70% vacuum, I can see, and
which is at 5 bar. So that's exactly on the spot.
So what actually happens on the cardboard material? I see that you have prepared some kind of a drawing here.
Yes, what happens with a material like cardboard or similar objects is that it will always leak through the material.
Through the material, yeah.
Which we call permeability, as a nicer word. But will also leak under the lip or the surface.
So there's like a surface leakage.
Yes, and that could be compensated with the cup or the lip itself. But the leakage through you can't do so much about. You have to compensate that with flow.
And I can see on these materials that, one is probably going to leak much more through than the other.
Yes, most likely.
Yeah.
The material itself, the cardboard itself, where it's produced, what type of material it is always a factor in that.
But let's do a quick test just to see the difference. Here is which one I think is quite smooth, and I don't know what the leakage through is, the permeability, but let's see what happens.
These type of cardboard boxes that are painted are actually the ones that most likely are the best. So you get fairly decent vacuum.
62% of vacuum. And let's take this one.
Get a little bit less.
A little bit less, but almost close to 62 also.
But this is a very durable box. I can feel that when I touch it.
Let's take.
And this one
it drops a bit.
Drops a bit. And you can feel it also in the material that it is a little bit thinner.
And here I think it's more challenging material.
Yeah.
Yeah, definitely. You're down to 27.
This is most likely sometimes also recycled material that they have done
very porous.
Very porous.
And here is a very
textured.
Very corrugated.
It's actually a little bit thinner, but it's actually
36, so a little bit more than that one, but probably less porous.
Less porous through the material.
Very interesting. So just to conclude then, have to understand the leakage through the cardboard material, but also the surface leakage.
Yes. You have to be in control of that. Then you can start dimensioning your systems for your object.
Very good. Okay, Johnny. If I want to build a vacuum system, what should I do then? What are the first steps and what should I think of?
The first thing to test is to find the right type of cup for your material. So if you know your carton box, you should try it with different cups and a single source vacuum flow, so you can understand how much leak flow you have through the material. And in that way you can find your suction point or your lifting force ability with your suction cups.
Okay.
So let's do some trials on these.
And I see you have a red and a black cup. They're like typical cups for cardboard boxes.
Yes, these cups have been around for a long time. Okay. And they're typically used for cardboard boxes.
Well, let's see, what do you get with the...
So let's run this and see what happens. You should be reading...
Very equal.
Quite equal.
No difference.
No. And this is because this material here is
it's a pretty
sealed.
Good cardboard material.
Yeah,
let's take good. B then. Yeah, also very equal, 61%. C.
The more we run...
D. Here we start to see more deeper vacuum with the red cup, so more lifting force then.
And this is because the red cup is softer in its material. It has more capability of sealing off the wrinkleness of the cardboard box.
Yeah, and here we see a huge difference.
Yes.
And this is really, here it's a lot of surface leakage, I can guess.
Exactly.
Wow.
You have the same size of the cups here,
I see it.
which means that it's actually the surface
Yeah.
leakage that you see in reed. These are in polyurethane, and those are in, the red one is in silicone, and the black one is in chloroprene.
Chloroprene.
Nitrile chloroprene. Let's give it a run. And you should see a slight difference.
I
very
see
little.
the green and yellow is a 63%, so a little bit higher than all the rest, but very small difference. Yeah, get a little bit more with a green yellow. That seems to be a nice cup. See, 59 and 56. So yeah, I think the green is more on the same level as the other two.
And they should be, because it's about the same stiffness.
And here comes the more tricky one.
This will be more challenging.
Wow, big difference.
And here you will see a big difference
difference.
between the green and the yellow here.
Yeah, even more. You're up to close to 47 and 25, yes.
And here you can see it's exactly like the other cups. They're the same size.
Same
So
size.
the leakage through is basically the same, but this one seals off better.
So it's really the surface leakage that yellow lip is sealing off so well.
Exactly, and it actually also creates a better controlled area that actually goes thinner.
And
or
20%
smaller.
difference in vacuum, that is also a big difference in lifting force.
A huge difference, I would say.
Difference.
As long as
good to see how it performs.
Yeah, see what it's like.
Oh, then the green and yellow BX is much better.
Yeah.
So if we take this one.
It tends to be able to seal off a little bit better.
Yeah, no, still.
MX cups is very good, but the more wrinkled surface you get.
No, still much better with that. But it's okay. I mean, it's. No, it's still better performance from the. Yeah, actually here the multi-purpose has been better.
Here it can actually seal better to the surface.
Yeah, interesting. Yeah, but that's good to know. So the cup for the cardboard box is definitely that one.
Absolutely, and it will last longer also because it has a much thinner or thicker lip. This one is extremely thin to compensate on plastic bags. So, but it works. It works good.
Let's stay with that one then, because this number C is actually the cardboard I have a project for right now. So if I want to dimension a system, how do I do then? We have picked that cup now.
We have picked that cup.
So what is the next step?
So now we need to understand how much compensate flow, the flow you need to compensate for, you need to achieve in this system per each cup. So what we do is understanding how much the vacuum level is. And here you can read
spot on 60.
So it's 60% of vacuum or 60 kPa. And knowing this engine here, the coax that we're using in here at 5 bar of compressed air.
You are feeding with 5 bar.
I'm feeding with 5 bar. And then we can actually go into our charts.
So then you have a chart with 5 bar feed pressure for that engine.
Exactly. So you look at the 60 kPa vacuum, and at 5 bar line, you can read that we're actually flowing 0.08.
So we have to compensate for a leakage that is 0.08.
Exactly.
Wow.
This leaks, the metal didn't leak, which means that you can reach maximum level of vacuum.
Okay, that's not so difficult.
No, so each cup needs a compensation of
so the leakage through this is 0.08 liters per second.
At 60% of vacuum.
With that engine.
With that engine, exactly.
Okay, Johnny, so now we know the leakage through the material with the test we did. But in reality, we quite often work with this central vacuum pump. Our customer prefers to have a central system. It can be due to weight or other things that they rather go for a central ejector. How do we think when we dimension? And of course, as you know, we want to move fast with the robot, so we want to start the movement quite early, as early as possible.
In general, you should always, the weight of the box, you know that you want to move fast.
Exactly. I forgot to say that, but the box is 5 kilo and it's this material.
This material.
The one we tested,
So that means that we know the cup we want to use. We tested this with this little equipment here. So this cup for this material, you know the weight of 5 kilo, and you
kilo.
want to go fast.
Yeah.
You should at least calculate with a safety factor of 4.
Safety.
And then the gravitation, of course, to get it in Newton. So,
and how deep in vacuum do I need to go?
You should always try to go under or deeper than 40 kPa. Calculate with that.
Yeah.
And then if you get more, good.
Yeah.
But that's the least
It's
amount.
a good rule of thumb.
Yes, try to stay under that or deeper. And in some bad carton boxes, it's impossible to get there, but that's a good rule of thumb. And if you have that, your box is weighing 5 kilos, so 5 times 4 in safety factor times 10 or 9.82, you get 200.
200 newtons.
So you need 200 newton to move this box in this speed. So how do you get there with this cup? Well, first you need to understand what is the performance of this cup at 40 kPa.
Yeah, and I know you don't show that data in your...
No, exactly. We have lifting forces in 20 kPa and
60 kPa.
But it's quite easy to draw a line in between this. So we know the lifting force in 20, you get 32 newtons, and at 60, you get 56. Reasonable value in between would be 44, or just under 40, or below.
So then I get 44 at 40 kPa, which was a good starting to start move the robot.
So basically, if you take 40 newtons,
yeah,
you would need 5 cups.
5 cups.
But I would suggest you use 6, and then you have that extra amount.
Yeah, it makes a nicer system also.
Yeah, nicer setup, and normally it evens out in a better way on a squared carton box. So you can perform place them in a good way.
Very good. So 6 of these cups. We knew the leakage flow. We did a test with that. But how do I know how to dimension this? Because I know you can have different type of engines inside.
This you can configure in different ways, of course, as exactly what you say. But to understand that, we have to go back to our chart again to look at the specific
to the test
test we did.
Yeah.
At the test we did, we knew that we had a leak through this specific material that you want to handle at 0.08.
Running it at 5 bar.
Running at 5 bar. Yeah. So if we take that value, and we can round that up to 0.1. So it's easy,
0.1.
Easy to calculate. So we have our 6 cups.
We selected 6,
times 0.1. And then we move over to this cups, this suction, or this vacuum pump.
So we have to compensate for 6 cups, so it's...
So if you look at this chart at 5 bar, you actually basically go directly on 50 kPa. 0.62 is very close to 0.6.
Okay, but if I reduce the feed pressure to 0.4, then
you reduce the vacuum level to 40. So you will be somewhere in here between.
That's good.
And that's deeper than 40, of course.
And you think 40 is good, but I cannot go lower than that.
No, you should stay under or deeper than 40. Here you get a little bit more. If you run this at 5-6 bar, you actually go even deeper, which is good. And a centralized system like this will always have somewhat of a pressure drop, even if it's designed good. So you don't get that performance out at the cup.
So I might have 50 kPa here, but
in the cup you might have only
a little bit
40.
less. So it's good to go a little bit above. If I go for a unit like that, it's more...
Then you connect the cup directly to it, and then you don't have any pressure drops at all, basically.
So that's the best. Well, super pedagogic by you, Johnny. This is makes it easy to dimension a central system.
Good.
Very good.
This is a simple method to do it.
Before I leave, Johnny, one thing came to my mind. I mean, when looking at these cardboard materials of a bit better quality, there was almost no difference in lifting performance or vacuum level inside these 3 cups. They were all generating 60% or 60 kPa of vacuum. Why should I pick this one, which I know is a little bit more exclusive and good? What's your...
Well, in general, they perform...
What's your reason for that?
As you can see, they perform, as you say, the same. Yeah. Nitrile or chloroprene and silicone is a cheaper material, so that's basically the reason why. But this cup, which is very rubber-like, has a wear resistance that is almost 4 to 5 times more. So if you put this cup into your environment, it will last 4 to 5 times longer.
4 to 5 times.
the longevity is actually better, and that's what you're paying for.
I mean, for me, I'm an integrator. Maybe it doesn't really matter, but I guess the end user really care about that.
Absolutely, for the end user, it's crucial.
If it lasts 4 or 5 times longer,
Yeah.
and it's also good for the environment with the
Yeah,
sustainable products.
Absolutely, especially if you have carton boxes that wears your cup really fast, and it could be even more. So that's
Super good. So that, okay, it's worth paying a bit extra to get this. And I know on this more trickier cardboard, it was really outperforming the others.
And especially as you said, you're going fast as well.
Yeah.
It will wear more. So
One last thing. Sometimes in some environment, can be in any type of industry, it's really dusty. And also in this packaging line, dust comes and lays on the surface. And we have seen that it can be slippery. Do you have any tips around that? I've tested this cup also, and it's also slipping a bit.
Even if that cup lasts long, now these cups are new, they're not even used, so you can feel they're actually a little bit sticky.
Yeah.
But after a while in production, they will tend to be slippery as well.
Yeah, especially when it's dusty.
Yeah, exactly. And then dust meet dust, and after a while it can be slippery. And in shear forces, that it could be a problem. But there is a little tip that I will give you that I know that could work quite well. This cup was actually designed, not just this specific one, but this type of cup was designed for oily sheet metal in an automotive industry. But
that's the one we use for sheet metal, oily sheet metal.
Exactly. Yeah. But it actually works really well in these dust environments as well. When you have a lot of dust and this problem occurs.
And I guess if the surface is smooth and fine, then it will work.
It will actually go through the dust, or actually you have more area surface to get a better grip on. But of course, it also will use a little bit more vacuum flow to be able to perform.
Yeah.
So
but
you
it's
need
really
to compensate a little
good
bit.
to know when we run into this problem.
Yes.
We want to do high speed and it's super dusty.
It could be a good tip.
Thank you very much, Johnny.
Thank you, Joseph.
As I always say, I will be back.
Yes, you're most welcome. Come back.
Thank you.
Thank you. Bye-bye. Thanks a lot for watching and for all the nice feedback on the last episodes.
And don't forget to like and subscribe for more vacuum insights from J&J.